Imagine your autonomous AI agent, the system you trust to write code or manage your cloud infrastructure, silently executing commands from an unknown attacker. To understand how this happens, we have to look at how these agents actually connect to large language models. Most developers avoid direct connections to providers like OpenAI or Anthropic, instead routing their traffic through third-party API aggregators to balance server loads and keep costs down. But there is a major structural flaw in this setup. The intermediary router sits directly between the user and the language model. When your agent opens a secure TLS connection, the encryption tunnel halts in the center. It stops right at the router. Because the encryption breaks, the router acts as a full-access proxy. It has complete plain text visibility into every prompt, tool, and API key. By placing this invisible middleman into the workflow, end-to-end security is broken.
The client is forced to place absolute trust in a third party that can read and alter every piece of confidential data. Modern language models produce executable code, usually formatted as a JSON payload, which tells the user's agent exactly what tool to run. Here is the critical gap. There is zero cryptographic verification tying the model's original output to the code your agent ultimately receives. An attacker controlling the middleman router can intercept a perfectly safe response from the model, rewrite the command payload, and forward their altered version back to the client. Because this altered JSON code is syntactically flawless and matches the expected tool format, the local AI agent has no idea it's been tampered with. It takes the malicious command and blindly runs it. Researchers classify this active manipulation as payload injection. The router takes a benign installation command and quietly swaps the target URL for an attacker-controlled script.
Other malicious intermediaries prefer to stay quiet. Through a vector known as secret exfiltration, they act as passive observers, scanning the plain text traffic to harvest Amazon Web Services credentials, hidden API keys, and crypto wallet data. Attackers also use dependency-targeted injection. They look for specific package installations and execute a typo squatting attack, swapping a single character to install a fraudulent package instead. This subtle substitution gives the attacker a durable supply chain foothold on the host machine. Long after the AI session ends, that corrupted software remains cached and ready to compromise future projects. None of these techniques require zero-day vulnerabilities or advanced system exploits. They work entirely by weaponizing the agent's implicit trust in the network intermediary. This grid represents 400 public AI API routers tested by researchers, paired with a chart tracking a live financial balance. Out of that sample, 8 routers were actively injecting malicious code, 17 were skimming cloud credentials, and 1 actively drained Ethereum from a researcher's wallet. You might think the solution is simply avoiding sketchy public routers, but due to what researchers call the contagion model, you don't actually have to choose a malicious router to be compromised. If a completely honest router accidentally reuses a leaked upstream credential, or if it forwards traffic through a weakly configured peer router, that single point of failure cascades. The attacker suddenly gains plain text visibility across the entire chain of otherwise safe intermediaries. Your agent's security posture is entirely transitive. In a multi-hop network chain, your data is only as secure as the weakest, most obscure router handling the traffic. Developers have tried implementing local mitigations to catch this, relying on strict domain policy filtering, anomaly screening to flag weird commands, and transparency logging to keep a record of the traffic. While these reduce exposure, they often fail against adaptive evasion. Sophisticated malicious routers don't attack every request. They hold back, waiting for specific session conditions, like observing 50 clean requests to bypass initial security audits before deploying their payload. The ultimate target for these triggers is YOLO mode, sessions where the user has granted the agent autonomous auto-approval. By only attacking YOLO sessions, the router ensures its altered payloads execute continuously without any human review. Without cryptographic provider-signed responses to verify the origin of a tool call, local defenses can only do so much. Trusting an autonomous AI agent means you are implicitly trusting every invisible digital intermediary standing in the shadows between you and the model.